talk about the homework assignment submission tomorrow. Yeah, tomorrow is the deadline, right? Yeah. Let me give you some update about the deadline submission tomorrow. All right. All right, I need to change the pen color. All right, so for our homework assignment number 1, deadline. Remind you, tomorrow, February 19th, Wednesday. Yeah. All right. But since this assignment is relatively big, you need to do a lot of work. Yeah. You know, in order, some students, so probably the last a few days, struggling to, complete the assignment. Based on that situation, I like to give you, grace period. I mentioned, right? Yeah, grace period in the first class of the semester. I talk about that. Yeah, the grace period. But this one, I like to give you the grace period two days, all right? Yeah. 2 days, the grace period, okay? All right, yeah. So that means if some student submit by 21st Friday, no penalty, okay? No penalty. Yeah. But I encourage you to do early submission, because I don't want some students, they completed, but they just hold. Yeah, I don't like to see that, right? Yeah, for that reason, I give bonus points for, timely submission, okay? Yeah. Bonus points. Okay. Bonus points, 2 levels. All right. If submitted by the deadline, yeah, so this deadline, okay, yeah, then those students get 4 bonus points. Okay, all right. The second case, yeah, it's hard to write because near the bottom, hard to write. If submitted by, yeah, because if you use 1 more day, right, by February 20th, Thursday, but you still, yeah, so you only use 1 extra day. In this case, you get 2 bonus points. Okay, yeah. Then 1 more day, 0 bonus points, but no penalty. Right? Yeah. So that's the modified rules for you. Okay. Yeah. But try your best to complete it as early as possible, yeah, but with the information like that, yeah, because if after Friday, then I need to take a penalty, okay, yeah, each day, I need to take some points off as penalty, yeah, all right, yeah, try to make it, yeah, try your best to make it, yeah. Yeah, after you submit.
Just make sure it's due at midnight of those days. Is that correct?
Question? Sorry, can you repeat?
Is it due at midnight of those days?
Yeah, midnight. Yeah.
Okay.
Correct.
Just making sure.
Right. Officially, it should be 11:59 p.m. Okay. Yeah. That's the yeah. That's the official end of the day. End of the day. Yeah. But I will be flexible, okay? Yeah. If you're just a few minutes past that line, so I do not count as one extra day. So I give you some breathing room, okay? Yeah. Not that strict. Yeah.
Thank you.
All right. Okay, so that's the updates. Yeah. I hope every students can pick it up, yeah, because many students, they may not watch the video, yeah. Oh, in that way, probably I can post an announcement, yeah, because some students, they may watch the video very late, yeah, past the deadline, yeah. So I will post the announcement for those students. Yeah. All right, so let's continue our second half. Yeah. D.2. From free motions to forced motions. Free motion, no force, right? No force is applied, no extra force, yeah, because, some force we must have, right? But there are some outside added force, yeah. So we need to consider that case. Yeah, forced motions. Yeah. Yeah. So let's look at the role of forcing function. Forcing function. All right. Yeah. Here, look at this. We modified the system a little more. Okay. Yeah. I mean by adding more and more terms into our original system. This time you can see we added this R of t force function. Yeah. R of t force function. Yeah. All right. So here you can see we will get a non-homogeneous second order linear ODE. Yeah. In this case. Yeah. All right, the free motion, yeah, the force term is 0. Okay, yeah, this is the force term. Yeah. Here we do not count the, Hooke's law, that force we do not count it. External, yeah, here you can understand this way. Internal force and external force, yeah, because these two we treat it as internal forces, so we do not count. Yeah. And then we only consider the external forces, yeah, as the, about free motion or not. Yeah. All right. Yeah, so free motion, that's the homogeneous. This means no external forces. Okay. Yeah. Only internal forces. Yeah. Then we add external force. Yeah. All right. Yeah. So we get a forced motion system. Yeah. All right. And name of this function, forcing function. Yeah. All right. And another terminology we mentioned before, input, right? That R function we treat it as the input. Yeah. So with the input forcing function applied to the system, yeah, mass spring system specifically, yeah. So then The solution is the output. Yeah. Yeah. All right. Yeah. Yeah. And or response of the system to the driving force. Yeah. All right. Then another important concept we need to study for the system like this. Yeah. Model, resonance. Yeah, this concept. Yeah. In our solution, so we need to consider this phenomenon. Okay, resonance. This phenomenon. Yeah. Some of you may heard of this phenomenon in your physics class, yeah, or in your real world experience. Yeah. Yeah. It is important. Yes. So here we need to study. Yeah. All right. Periodic external force. So here the question is, for the external, the forcing force, there are two types, periodic and non-periodic, right? So one type is non-periodic. Another case is periodic. Periodic. Yeah. But for the periodic case, then you need to consider this phenomenon. Resonance, this phenomenon. For non-periodic, you do not need to consider. Okay? For non-periodic, you're fine. Yeah. So the system, the solution, everything is all right. Yeah. But for the periodic forcing force, then this resonance problem you have to seriously consider. Yeah. Because there is some potential damage to the whole system. Potential damage caused by this resonance problem. Yeah. So let's look at that. All right. Here we imagine we have a periodic forcing force. Yeah. F0 times cosine omega t. Yeah. All right. Here you can see this omega constant. This constant is related to frequency. But this frequency is the frequency of this force, external force. Yeah. Remember I mentioned that natural frequency of the system, right? The system has its own internal frequency. So we call it natural frequency. But your forcing force could have some frequency, yeah, different frequency. Okay? Yeah. So these two frequencies, when we compare these two frequencies, yeah, so we will see, yeah, how do they relate it to this resonance problem. Okay? All right? Yeah. Yeah. So let's consider the non-homogeneous ODE. Yeah. So this time, yeah. So we get this not very complicated, right? Yeah. So this equation, so we know how to solve it. Yeah. So not very complicated. Yeah. All right. Next, yeah. Next we need to solve it. Yeah. So here I just give you the background of the system. Yeah. But next we need to find a solution. We need to solve the system. Yeah. After we understand this system, yeah, let us solve it. Yeah. D.3, non-homogeneous second order linear ODE. But when we solve it, yeah, we want to connect to the, forced motion mass spring system. Yeah. Yeah. So we want to interpret the solution, yeah, in that system. Yeah. All right. Yeah. Solving this one, yeah. So the general solution, yeah, contains two parts. Yeah. The first, YH homogeneous. Yeah. The solution for the homogeneous system. Okay. Yeah. So you replace R function by 0. Yeah. Homogeneous. Yeah. But this P, Y sub P, particular solution. One particular solution, but that particular for the non-homogeneous system. Yeah. So you need to find a one particular solution. Yeah. Non-homogeneous system. Yeah. All right. Yeah. So then, in this way, you can use this general solution to represent any particular solution. Okay? Any particular solution. Yeah. Here, the reason we can do that, yeah, remember, we have one theorem. Yeah. So we have one theorem before. Yeah. When we talk about existence and a uniqueness theorem of second order linear, that ODE. Yeah. So we have a result saying no singular solution, right? So here, this means because we have that result, there is no singular solution. So that's why we can represent all particular solutions. Okay? If we have a singular solution, then you cannot represent it in this way. Okay? So no singular solution can be represented in this way. But fortunately, for second order linear ODE, so we do not have any singular solution. Yeah. All right. Yeah. Okay. So then YH. Yeah. So we solve the homogeneous system first. Yeah. Yeah. All right. Yeah. So then a non-homogeneous, a general solution. Yeah. 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 Here, no singular solution. Yeah. All right. The question: how to find a YP? Yeah. Because solving this one relatively easy. Yeah. So we have some methods we can use to solve. Yeah. But in order to get a final solution, you need to find one particular solution. Yeah. All right. Two methods. Yeah. One simpler, the other more general. Yeah. Method of undetermined coefficients. All right. So here, we are do preparation. Yeah. When we solve that the system, right? So the forced motion system. Yeah. So here we mathematically, so we do some preparation, yeah, before we can solve that system. Yeah. All right. So the first method of undetermined coefficients. Yeah. All right. For constant coefficients. Yeah. All right. Simplified form. Yeah. Yeah. So let's consider this simplified form. Yeah. All right. A and B constant. Yeah. So we know the solution. Yeah. All right. Yeah. So here, when the solution is, right, yeah, exponential function. Yeah. So here, the solution, that solution, the exponential function. Cosine, sine, or sum of the products of such functions. Yeah. Right. Yeah. So here, yeah. All right. So here, so the description here. Yeah. So what's the meaning of that? Description here is, yeah, because here we work on undetermined coefficients. Yeah. Yeah. Remember the goal. Our goal, we want to find a particular solution. So this is our goal. Find this particular solution. But when you need to find a particular solution, you need to, so here, okay, yeah. One way, yeah. So let me start from our old experience a little bit. Yeah. In our old experience, remember, we had some similar experience that we need to find one particular solution, right? Yeah. So remember that, yeah. But at that time, we guessed that particular solution, right? The old time, because we do not have any specific method, right? Yeah. So if you look at our old notes, at that time we guess a particular solution. Okay, yeah. But it's hard, right? When your equation is simple, then you can guess it. Yeah. But most of the time your equations may not be that simple. So it is not realistic to guess a particular solution. All right. Now we want to improve our guess. Yeah. So we want to do some action. The action is related to guess, but it's not completely guess. It's you can treat as a halfway guess. Okay, halfway guess. So here, what's the halfway? Yeah. First, you imagine that there are some special structure for your particular solution. Yeah. The particular solution, first you guess the structure. Okay. Yeah. Here. Yeah. So you guess the structures of the solution. Okay, yeah, structure. Guess the structure based on your experience and analysis. Yeah. So here, people, yeah, because our goal, we need to work on a particular solution here. Yeah. First question, what is the special structures this solution should have? We want to answer that question. Special structure. Yeah. Yeah. Could be different structures. Okay. Yeah. Yeah. Special structures. Yeah. Here, this, the last two lines give you the special structure. Okay. Give you the, based on the experience. Yeah. So these, the structure description, we call the last two lines the structure description. Yeah. By the experience. Experience. All right. Yeah. All right. So based on the experience, yeah, we feel these structures could be used. Okay, these special structures could be used when we formulate that particular solution. Yeah. One is exponential function. Yeah. Yeah. Exponential function, that's e to the some t, right? T related terms. E to the some t. Okay. Yeah, you can say ct or whatever, right? Yeah. Yeah, exponential function, because it has this function has the property, its first derivative, second derivative, all have the exponential form, right? Yeah. If you take the first derivative, its second derivative, you still get an exponential function. Yeah. So that's some nice thing. Not nice thing. So you may like to have. Yeah. All right. Then power function, power of x, yeah, x to certain power, yeah, then this function has the property, its derivative, second derivative, also power function, right? Yeah. So you similar structure, power function. So then, you can use there, all right? Sine, cosine, yeah. So it has the property, derivative from sine to cosine, cosine to sine, right? Yeah. So they also have the property that derivative, second derivative also can be represented in sine, cosine. Yeah, sine, cosine. So it's also a good candidate. Yeah. Or sum or products of such functions. Yeah. Sum, yeah, by the linearity, yeah, because this is a linear equation. Okay, yeah, linearity. When we consider the homogeneous part, the linearity property can be used. So based on the linearity, we can use sum. Yeah. Yeah. And sometimes the product of such functions also, yeah, because the product form, although here we cannot use the linearity, but the property, the product, when we do derivative, second derivative, they also have these structures, right? Yeah. The reason we can consider the product of these functions, because their derivative, their second derivative, they also have, the structure given here, yeah, given in the candidates listed here. Yeah. All right. Yeah. So the reason here we guess the structure. Yeah. So here, by experience, yeah, yeah, these functions have derivatives similar to itself. Yeah. So that's the reason. Yeah. We can try these special functions. But when you try these special functions, what are the coefficients, right? Yeah. So when you take sum, yeah, so you need to add appropriate coefficients. Yeah. So that coefficient's undetermined, because nobody can guess appropriate coefficients. Yeah. So that's why we set coefficients unknown. Yeah. This method, we need to determine appropriate coefficients. Yeah. So for that reason, we have this method. Okay? Yeah. So here you can see, yeah, it's not magic. Yeah. So it's based on the understanding, yeah, of the problem, yeah, and based on the experience, yeah, and we also will do analysis. So we, come up, yeah. So some mathematicians, yeah, so early time mathematicians, so they came up with this idea. Yeah. All right. Yeah. So D.4. Yeah. So let's implement this idea, method of undetermined coefficients. Yeah. So we can use some example to see, yeah, how to implement that idea. Yeah. All right. Input exponential function. If that little r function, the input function is the exponential function, now you can see, yeah, your particular solution should have the related structure, right? Exponential function, related structure. Yeah. All right, let's look at this example. Solve the initial value problem. Yeah, this one. So the input function has the, special exponential function here. Yeah. All right. Now you guess your particular solution, but when you guess, yeah, you need to use some undetermined coefficients. Yeah. Yeah. The initial conditions. Solution. Find a particular solution. Yeah. So then we can easily write the general solution. Yeah. So this particular solution, yeah, then we use this form. So here you can see it's a product form. Okay, the C undetermined. Okay, so C undetermined. All right. Then the product of one power function, one exponential function. Yeah. The product of two functions. Yeah. Some people you may ask how do you know you can add that x squared, right? Yeah. So here, x squared because related to the second derivative. When you take second derivative, yeah, the s squared, that part becomes x, right? The derivative, x times some exponential function, the product rule. Yeah, so product of second derivative you take twice. Yeah. So the second degree, then first degree, so then then only exponential function. Yeah. So you have that. Yeah. And actually, later you will see actually one, yeah, because so here, look at this. Yeah. Yeah. So still the question, how do you know you can use this special form, right? Yeah. That question. Yeah. All right. So here, because here, in order to work on the left-hand side ODE, yeah, left-hand side ODE, yeah. So usually, yeah, the particular solution you can consider, yeah. So it is, let's say, yeah, more general case, A plus B x plus C x squared, then times this, same exponential function part. Yeah. All right. But this version, this is a more general version. Okay. But you have three undetermined coefficients: capital A, capital B, capital C. Right. But this is just a special case of that, right? Of that more general case. Yeah. So here, this one, the reason it dropped that A term, B term, yeah. Because if you can find a solution, only use that C term, then we just take it. But if you cannot find a solution, if you use this C term form, plug in, but at the end you couldn't find a solution, then you need to add more terms, okay? Then you need to add more terms with more undetermined coefficients, and hopefully the added freedoms, because when you add two more terms, you get added freedoms, and hopefully the added freedoms can help you find a solution. So that's the basic idea. All right. Yeah. So here, but when you start the first try, so you want this form as simple as possible. Yeah. So that's the the rationale behind it. Because you may ask people, why you select this form, right? Why you select this form? Yeah. So I try to expose the hidden analysis, yeah, behind that how people select this special form. Yeah. All right. Yeah. So let's do the work. First derivative. Yeah. Because after you select that one, then the work just as routine. Yeah. All right. Double prime. Yeah. So then you combine, all these related. Yeah. And you can cancel out the E function. Yeah. Same structure. So you cancel out. Yeah. Then you get a algebraic equation, right? Yeah. So this algebraic equation, yeah. So here, in this algebraic equation, only C is unknown. Only the C coefficient is unknown. Okay. All right. Yeah. Then, how to find the C? Yeah. So let me explain how to find that C. Yeah. In order to make this equality, yeah, because we want this equality holds, all right? Yeah. It's an equality, it's an identity, yeah. That means this is equality, this equality holds for any x, okay? So here the meaning, we have this equality, yeah. Meaning, okay. This equality holds for any x. Okay. It's not for one particular x, for any x. What is x? X as a real number, right? Real number. Okay? Yeah. This equality must hold. All right? Yeah. So that's the meaning. All right? Under this understanding, we need to find the C value, capital C value. Okay? All right. So let's do it. By comparing the coefficients. Yeah. Why by comparing the coefficients? Yeah. Here, because look at the left-hand side of the equality and the right-hand side of the equality. Left-hand side equality, it is a quadratic polynomial, right? It's a quadratic polynomial. How about the right-hand side? Right-hand side, it's a constant, right? -10, constant. So the question, is it possible that one quadratic polynomial is the same as a constant? Non-zero constant? Yeah, left-hand side is a quadratic polynomial, but right-hand side it's just a constant. Okay? Yeah. The question, yes, it's possible. Okay? Yeah. So here, let me consider this case. Ax squared plus bx plus c. Is it possible this quadratic equation equals some non-zero constant? Here, let me put 10. For all x, for all real number x, yeah, think about that, okay? The question is yes. Yeah. Why? Because when a equals 0, when b equals 0, when c equals 10, is it correct? Right? That's simple, right? Yeah. A, yeah, that coefficient. Because if a is non-zero, then it won't happen. So the equality is never true if a is non-zero. If b is non-zero, then the equality never true. Okay? Yeah. Only when a equals 0 and the b equals 0 and c equals 10, then this equality always true. All right? Yeah. So that's the based on this simple example, so we can compare the coefficients. Okay. The coefficient is the, yeah, so because when you write this equation, you will write something times x squared plus something times x, then plus something equals the -10, right? Yeah. This first parenthesis must be 0, the second parenthesis must be 0, then the third parenthesis must be -10. Okay? Yeah. Under that condition, we can find the solution C1, C value, capital C value. It must be -1. Yeah. But fortunately, in other words, when capital C equals -5, we are very lucky. The first parenthesis equals 0. Second parenthesis also equals 0. The third parenthesis equals -10. All these three parentheses satisfy the requirements we need. How can that be possible, right? How can be that possible? Yeah. All right. Do you think it's a lucky solution? Yeah, it's a lucky solution. Yeah. Because if we are lucky, yeah, because most of the when you when you solve an equation, most of the time we're not lucky. Okay, that's the rare time. The lucky case is always the rare case. Yeah. So most of the time we're not lucky. Okay, most of the time not lucky. Okay, but in the general unlucky case, general. Yeah. Don't worry, when you have an unlucky case, you need to use this form. You need to, use capital A, capital B, capital C. Then you have the enough freedom to make the first parenthesis 0, second parenthesis 0, third parenthesis equals any number you like. Okay? Because you have 3 freedoms. See? A, B, C, 3 freedoms. So you can address 3 conditions. The first parenthesis condition, second parenthesis condition, and the third parenthesis condition. If we are not lucky in the general case. Alright? Yeah. Alright. So that's how I explain. Yeah. Otherwise, people may ask, why you select this form. Yeah. Alright? Yeah. So then we can write the particular solution YP. Yeah. Then the general solution, yeah, by characteristic, yeah. So yeah, here characteristic and the 2 equal roots, right? So the solution is in this form, C1, C2. Okay. Then you use the initial condition to determine. Initial condition. You can find the little c1, little c2 value. So that's how you solve this equation. Okay? Yeah? Yeah. So I hope after I explain this way, there is no magic. Okay? Yeah. Yeah. Because if I do not explain, I spend a lot of time explaining. So how people can get this particular solution. Yeah. So then later you won't treat this as a magic form. Okay? Yeah. Because this one, you need to know most of the time it won't work. Okay? Only when you are very lucky it works. Yeah. Most of the time, yeah, you won't make it work. So you need to try this that way. Okay? You need to try that way. Yeah. Then this way, because you have three freedoms. 3 freedoms. So it is guaranteed you can find a solution of the making that equality holds all the time. Yeah. All right. Yep. Okay. All right. Yeah. So because we do not have enough time, so I do not want to do a new slide. So let me just say a few words before we end today's lecture. Yeah. This example, because we learned the Laplace transform, right? Yeah. So if you want to try, so you can also use Laplace transform to find a solution. Yeah. So because our basic formulas, should be enough. Yeah. And then you can compare with the solution. Yeah. So you have different ways to solving the same problem. You have different ways. Yeah. Then in the future, in our homework assignment or tests, sometimes I specify, I ask you. Yeah. So when I give you ODE, I will say which method you should use. Yeah. For example, if I may specify you need to use Laplace transform to solve this problem, or you need to use non-Laplace transform method to solve the problem. Yeah. Yeah. Sometimes I will specify which way to solve. Yeah. If I do not say anything, then you have freedom to choose. Okay. If I don't say, you know, Laplace or non-Laplace, then you just select your favorite method to solve. Okay, yeah. So, you know, so that's the, you know, general rule. Yeah, here. Yeah. All right. So let's stop right here. Yeah. All right. That's it. Yeah.